Okay, hello everyone, and welcome to the second of the gas processing tutorials on using OLGA. So in the first tutorial, we basically covered how to specify what it is that's flowing through your pipe, and we did that using MultiFlash. In this second tutorial, what we're going to be doing is actually building a simple steady-state case in OLGA. So I'll throw up a set of steps that you can basically follow in order to build one of these for your own particular design. Okay, so when you open up OLGA, this is the screen that you're going to be seeing. Now, what you basically want to do to begin with is to create a new OLGA project. So we do that by coming up here and clicking on the Empty Project button. What this will allow you to do is to browse to a particular location where you want to store your OLGA project. So you can see I've just put mine on the desktop. This is going to be our tutorial OLGA case. And we can save that. Now what we can go ahead and do is to create an empty case which is going to be stored within that particular tutorial, or within that particular project. So what we have here then is the main OLGA UI screen. Now this has a number of different bits and pieces on it, and effectively what you want to do is to work from left to right. So we have a number of different components that can be added, and we can also switch this into a model view, which is going to tell us about what we've added into our simulation. We have our top bar here, which is going to allow us to, for example, duplicate a case that we've built, save or save as a new case, run our batch simulations, verify whether our existing simulation actually works, extract results from the simulation once it's run. And if you lose any of your windows, you can check this little view tab up in the corner here. So in this central space here, we actually build our OLGA simulation. And then finally, on the right-hand side here, this is where we specify individual components within the simulation itself. So what we're going to go ahead and do as part of this tutorial is to build that example steady-state case that is in your tutorial slides. Okay, so the first thing that we want to go ahead and do is to actually import the information that we had from MultiFlash and use that within our simulation. So what we do is we go down to the bottom here and we click on Model View. We click on Case, Case Definition, Files, and over here we can choose our PVT file. So this is what we created in MultiFlash previously, and this is our tab file. So what we want to go ahead and do here is to browse to our particular tab file. So you can see here that this has brought up our OLGA tutorial case, and what I've done is to put in the OLGA tab file that we generated previously. Now as a tip, when you're building your own simulations, you should give them more meaningful names than MF OLGA 1. So perhaps this might be labeled Reservoir A, Year 0. So we can go ahead and we can open that, and we have two options in terms of the way that we specify where these files are, absolute or relative. I would always suggest using relative because what this will do is allow you to copy-paste your entire OLGA simulation between different computers and have it just remember that the OLGA tab, or the OLGA tab file, is within the same folder as your overall project file. So we can go ahead and click OK, and now we have some sort of a fluid file which has been added to our simulation. So the first thing we're going to go ahead and do before we start drawing in our actual pipeline is to tell our simulation what that pipeline is made of. So we right-click on Library, we say Add, and we can add a wall, and we can also add a material. So firstly, this material, we can put in a number of different properties for it. So over here in our Properties window, we're going to say that this is a steel. We're going to give it a heat capacity of 500 joules per kilogram Celsius. We are going to give it a thermal conductivity of 26. Now the way that I changed the unit without changing the value here, if you see we go ahead and change the unit, that'll automatically update the actual value in it. But if you simply type in the value and then hold the Shift key while changing this unit, it will not change the actual value. Then we're going to have a density, 7850 kilos per meter cubed. And this is basically our steel material specified. What we'll do then is to take a look at our wall, and again, we need to give it some sort of a name, so let's call this our exposed pipe. This can have a thickness of 1 inch, so again we hold shift, and we change that to inches, and that stays as 1 inch. Now the material, that's what we just created. So we click here, and we add the steel material. So now we have a material, and we have a wall which is made out of that material. So what we can begin to do now is to move that picture of our case into OLGA itself. And in order to do this, we're going to begin to add components. So we go down on the left-hand side here, and we click on Components. And the first thing that we're going to do is to add in a closed node. Now what this basically does is to just prevent any fluid from flowing back along past this location. So this is going to be our well. What we're going to then put in is an internal node. So this is some intermediate point in our pipeline, and this is going to be our wellhead. What we can do then is to connect these two things with a flow line. So the way we do that is to just hover over our well until we see this little hand pointer here, and we can hold down our click and drag that onto the wellhead and just let it go, and there you can see there's now a connection between these two different things. We can drag the name of this flow path out the way, and what we're going to do is to call this our wellbore. Okay, what we can do now is to complete the picture that we actually had for this particular system. So we're going to add another internal node, and this is going to be our riser base. And then the final thing that we can do is to simulate our top sides with a pressure node. This is a boundary condition, and this is going to be a separator. There we go. And again, we can now connect these things here with flow lines from here to here, and then our riser in this section. So this is going to be our flow line, and this little pipeline here is going to be our riser. Okay, so then what we want to do is to go ahead and actually specify what's going on with these particular sections of pipeline. So to do that, the easiest thing is to go back to our model view, and now we can see a whole list of what is actually contained within our particular simulation. So what we're going to want to do is to edit the flow paths edit each of these flow paths. So what we want to go ahead and do is for each of our flow paths, we want to click on pipe 1, and we want to tell it a number of different important properties. So here, our roughness, we'll leave that as our default. We can change what our wall is made out of. So here we can select our exposed pipeline. Then we can also specify some properties of the actual pipeline itself in here, or we can edit it in another tool, which we'll have a look at in a moment. So we set our exposed pipe for our flow line, for our riser, and for our wellbore. Okay, so now what we're going to do is to actually edit the geometry of our particular flow line segments. Now the easiest way to do this is to just hover over the pipeline and double click on it. So you can see this initializes something, and what it actually does is to create a second window that'll pop up on your desktop. If I drag that over here, what we can now see is a picture of the geometry of the flow line, or of the wellbore that we're dealing with. So this is the height and this is the length. And each of these segments here simulates or represents one section of the pipeline that's going to be simulated. So you can see at the moment there are only going to be 2 sections that are simulated for this particular system. Now in order to change that, what we do is up the top here, click on our geometry, and then what we can do is to actually input the specifications that we'll put in for our system. So let's have our unit. If we right click on here, let's change these to feet, as that is how they were specified. Okay, so our beginning X point here is going to be 6, our Y is going to be 5280. And as you can see then, what it's done is to go ahead and just use simple trigonometry to calculate what the length of the pipeline is. What we can also input is the number of sections that we wish the pipeline to be simulated in. So if we set that to 10, you can now see that we have 10 sections, and this is the length of each of those sections. We're happy with our 10-inch diameter, we're happy with our roughness, and we're happy with the fact that this is now an exposed pipe. So we can go back to our first tab here, and now you can see there are actually 10 different sections that are being simulated together for our wellbore. So now what we can do is to go ahead and close this, and yes, we wish to use this particular geometry. And if we were to go back and double click on this once again, you can see that yes, it has retained this particular knowledge of how we've specified the flow line. Okay, so now that we've specified our wellbore, we can go ahead and specify our flow line. So if we take a look at our system diagram, then our distance, our increase in height is going to be 30 feet. And our length of this section of flow line is going to be 30 miles, which is 158400 feet. Okay, and again, you can see our overall length in meters, and we can specify, again, 10 sections here. You can see, obviously, these are much larger sections. So, effectively, this then comes down to how accurately or with what resolution do you want to be modeling your particular flow line. And this is going to depend on the given system that you have. Given that this is just a flat section of flow line, let's start out like this, and we can always refine it further later on and further down the line. So we can go ahead and save this, yes, and then we can edit our riser geometry. So, our riser geometry, we're going to have a height in feet of 650, and we're only going to have a 3-foot deviation in the x direction. And again, 10 sections. We can go ahead and close this, and that has now updated the geometry for our entire flow line here. Okay, so now what we want to do is to think about what it is that we're actually simulating. And in effect, there are a couple of different things that you have to consider. Now, firstly, what is the pipeline going to look like? So that's what we've got here. Secondly, what's flowing through the pipeline, and we specified that using our MultiFlash PVT files. Thirdly, what's going to be the driving force for flow along this pipeline, and we'll get to that in a moment. And finally, how much energy is the pipeline going to bleed off to the environment as the fluid flows along it? So that's what we'll have a look at right now. So the first thing that we want to do is to go ahead and change the way that we deal with heat transfer within OLGA. So what we're going to go ahead and do is to go into our case definitions. We'll take a look at options. And what we're going to do is to set our temperature away from wall to U given. Now what this means is that when we're doing heat transfer calculations, we're just going to use an overall heat transfer coefficient rather than doing a calculation which takes into account convection and conduction through the wall. So, what we can go ahead and do now is to add heat transfer modules to our particular flow paths. So if we right-click on the flow path, we say Add, Boundary and Initial Conditions, and Heat Transfer. Then what we can do is to right-click on this and say Duplicate to All. So we can now see that we have a heat transfer module for each of our individual flow paths. So firstly, in our flow line, you can see we have selected here, this is going to be flow line, heat transfer. This is going to be applied to pipeline 1. We say OK. The way that we're going to interpolate our ambient temperature across the entire pipeline is going to be section-wise, and we're going to say that our ambient temperature is 40 Fahrenheit. Now finally what we're going to do is to set up our overall heat transfer coefficient, which is our U value here. We are going to use 4 BTU per foot squared per hour per Fahrenheit. So moving on to our heat transfer for the riser, this is going to be riser heat transfer. Again, this is going to use pipe 1, and this is going to be specific to pipe 1 within the flow path of the riser. So this pipe 1 means using the riser flow path, whereas in the previous heat transfer module, where we were looking at the flow line, that was specific to the pipeline 1 geometry for the flow line itself. So, as our riser is interpolated, we're going to use changing with the length, and our inlet ambient temperature is going to be 40 Fahrenheit at the bottom of the riser. But by the time we get to the top of the riser, we've actually increased our temperature at the sea surface to 80 Fahrenheit. And what we're going to do here is to have a much higher heat transfer coefficient for our riser. Now this just leaves our wellbore, and again this is going to be our wellbore heat transfer. We are again going to interpolate by length because we're going to have changes in the ambient temperature as we move along the wellbore. So in our reservoir, we're going to have 200 Fahrenheit. By the time we get to the top of the wellbore, we come down to 40 Fahrenheit. Okay, and given that our wellbore is transferring through rock, we're going to have a much lower heat transfer coefficient. So we'll use 0.2 in this case. Okay, so now we've specified what the pipeline looks like, and we've specified how fast heat is going to be lost from it. Now, previously using MultiFlash, what we did was to specify what's going to be flowing through the pipeline. But now what we're actually going to do is to generate that specification within OLGA itself. So what we're going to do is to look at our wellbore flow path, and we are going to right-click, and we are going to add boundary and initial conditions, and we will insert a mass flow source. So you can see this is our mass flow source on the wellbore here, and we have our properties on the right-hand side. So what we want to do is to say that this is going to be specified from time 0. This is a mass flow source. This is going to be from our reservoir, so it's going to have a reservoir conditions of 200 degrees Fahrenheit. And let's use 20 kilos per second as our inlet mass flow rate. Now, where is it that mass is flowing in this particular riser? Well, the pipeline is going to be pipeline 1, because that's the only one that's available for our wellbore. And the section is going to be section 1. So what we're saying here is that we have reservoir fluids entering from the bottom of the wellbore. Finally, if we take a look at our phase distribution, you can see these values here are set to -1. And what that means is that when we introduce our MultiFlash fluid file, it's going to specify what the actual gas and water fractions are using that MultiFlash fluid file. Okay, so now that we know what's coming, or what's at our inlet here, we have to tell OLGA what it is that's actually flowing in each one of its pipelines. So what we're going to do is to look at our model view again, our flow path, then we're going to look at piping, and we're going to click on branch. And in our properties, you can see that we have not got a fluid specified. So what we're going to do is to change that to black oil with water. So this is the name of the, or this is the fluid ID associated with that MultiFlash tab file that we initially created. So this is black oil with water. And what we have to do is to tell each and every one of our different sections what is flowing in it. So we have done this for the flow line. We have to now go to the riser and say, once again, we have black oil with water. And in our wellbore, this is also black oil with water. Okay, now for this simple system, we've just got the same fluid file in all three of these sections. But what you'll see then is when you have, for example, mixing fluids, you're going to have to create new tab files and new fluids when you have mixing within your system. And we'll go into that in a little bit more detail in tutorial 3. So we've now done everything except for telling our system what the driving force for flow is. So we've told it that there is a given amount of mass being pumped into the system in our source, which is 20 kilos per second, but we don't know anything about what is happening at the outlet condition. So what we can go ahead and do is to click on our separator, and we can make some specifications down here in our pressure conditions. So you can see that we require a temperature, and this is going to be our separator temperature, which was specified as 80 degrees Fahrenheit. We also have a pressure, which was specified as 300 psia. Finally, we also need to know what the fluid is at the outlet. So we're going to use, again, the black oil with water. So I'd like to note at this point that the particular way that we've specified this system is using this mass source. But what we can also equivalently do is to use one of these pressure nodes as our inlet, because this tells us what the temperature, pressure, and fluid composition are coming into the system. So if we just have a pressure node at the inlet and a pressure node at the outlet, what OLGA is going to be able to do is to work out what that driving force or pressure differential is, and it'll calculate a mass flow rate for us. And this can be useful depending on how your particular system is specified. Okay, so at this point we'd hope that everything is specified within our system. However, we still have this little red not runnable down the bottom. So we can use this verify function to tell us what it is that we've actually missed. So we can see in our wellhead we haven't yet specified our fluid. And if we click on this little green arrow here, it'll take us to that missing fluid specification. So what you can see is that while we'd specified the fluid in all of our flow lines and in our outlet, we also have to specify it at the intermediate nodes. So we've added our fluid now for our wellhead as black oil with water, and at our riser base. So you can see now we are ready to simulate. We can once again click that verify button, and verification has succeeded. So it's now possible to actually run an OLGA case. Okay, so we now have a working simulation as verified by our button here. Now, what we have to do before we actually run OLGA is tell it which variables we'd like it to remember. Because OLGA is generating so much data, it's not going to automatically remember every single variable and how that changes at every point in time and space along the pipeline. So what we have to do is to use these output functions to determine which variables we would like it to keep a track of. So we have two types of entities here. We have profile data, and this tracks the way that the pipeline changes along its profile, which is to say along its length. And then we have our trend data, and this tracks how a specific variable changes at a given point along the pipeline. So you can see the way this is set up initially is that we have two trend datas and only one profile data. Now, if you wish to track how variables change at multiple points along the pipeline, you can either create multiple trend data files here, or alternatively, you can just delete the excess one, and you can input for your given section that you would like to track, say, the beginning, middle, and end of the pipeline. This is now going to track whatever variables you've selected up here at these 3 points along the pipeline. So what we're going to do is to choose to track a couple of different variables by clicking on our profile data. Then over in our properties tab we can choose our given variable. What we can do here is to search either by description or keyword or key value for our given output for the different things that we would like to look at. If we use this little check mark here, it'll show us which ones are currently being tracked. Okay, so what we'd like to take a look at for this particular simulation are the holdup, the flow regime, the pressure. We don't want to have a look necessarily at the overall heat transfer coefficient because we know what that is as we've specified it. We can take a look at the amount of gas that's flowing through the system, the amount of liquid or oil that's flowing through the system, and the fluid temperature. Then we click OK, and that saves the variable selection that we are using. What we can do then is, instead of changing this individually in all of our different flow paths, is to just delete these other profile datas, and we can duplicate to all from whichever one of these we choose. And you can again see that we no longer have that overall heat transfer coefficient selected within this particular profile data that we are tracking. Okay, so we can do the same thing for our trend datas. Let's delete these excess ones, and let's just look at editing the one within our flow line here. So again, let's track at these 3 points the following variables. So what we want to do is to have a look at the holdup, the pressure, the temperature, and we also then want to take a look at the flow regime. And as we can see here, we've searched for the description of flow regime, and this is our ID down here. And if we press OK, we can see that ID has now appeared in the variables that we are tracking. So again, we can right-click and duplicate to all. So now we should be tracking the holdup, flow regime, pressure, flow rates, and temperatures in all 3 of our sections in the profile, and we should have trend data at 3 points along our pipeline. So we have one final step before we actually go ahead and run our simulation, and that's to tell OLGA how long we want to simulate for. So what we do here is, once again, in our model view, we take a look at our case, and then we take a look at case definition, and in integration, we can set our end time here that we want to be simulating to. So let's say that we want to simulate this pipeline set for 1 day. It's also important to check within options that we are also simulating the steady state profile for OLGA. So what this means is that before OLGA runs its detailed calculations, it's going to run a quick once through steady state calculation in order to get a good first estimate of what is exactly going on within the system. When we get to transient calculations in tutorial 4, we'll be turning this option off. So we now have a simulation which is ready to go. We've told it what we want to actually be extracting from the simulation, and we've told it how long we want to be simulating for. So what we can go ahead and do now is to press the Run Batch button up here. Okay, so we've gone ahead and pressed our Run Batch simulation, and what's actually happened in this particular case is that we've gotten an error from OLGA. So you can see pressure above table values, and these are the pressure values that we've reached, or the pressure and temperature conditions that OLGA wishes to calculate, and this is apparently outside the range of conditions that we've given it in our table file. So what I'm going to go ahead and do is to edit our table file, and we'll just expand the range of conditions that we actually require for OLGA. Okay, so what I've gone and done is to rebuild the OLGA tab file, and what you can see in here is that I've replaced the original badly named tab file with this new one, tutorial blackoil.tab. So this is now the only fluid file that's being used by the simulation. Now usually what you would have to do is to then re-specify the names of all of these fluids throughout your system. But what I did was to just keep the name the same, black oil with water, for the case of this tutorial. Now in general, when you're running these simulations, I do not recommend doing that, because you would like to have unique identifiers for all of your fluids, especially when you've got more than one fluid that's going to be flowing in your system. What we can now do is to once again try and run our batch simulation, and if we bring the window over here, we can see that this time we haven't crashed at the start, which is a promising sign. And now we have simulation time elapsed, 10, 20, and it'll continue on in that manner. Now, some of these simulations can wind up taking quite a long time, especially once you enable the more advanced modules such as hydrates. But on a modern computer, you can expect an OLGA simulation, or at least a simple OLGA simulation, to run within the space of a couple of minutes. So, once this is finished up, what will happen is that OLGA will give us a little message saying simulation complete, press any key to continue. Now the important thing is that you don't press the enter key on your number pad, because it's a command window and that will try and edit something. Okay, so we've ended our simulation, and now what we can actually begin to do is to interpret some of that data that's come out of this. So once again, our outputs told the simulation what data it would like to save, and the way that we can then view that is by using these two plot tabs up here. Let's just take a look at a couple of simple profile plots. So we click on this, and this will bring up a new window which allows us to look at all the different variables that we've tracked. Now there are some helpful filters on this. So in our particular case, let's just look only at flowline variables. And then we can choose that we would like to take a look at temperature, pressure, and hold up across the entire flow line in terms of its profile. So we press OK. We can see that OLGA brings up a nice little profile plot for us to take a look at. So there are a couple of things that you can do here. We can view track values, and this will actually tell us very specifically what these values are as we track our mouse across the line here. Now, one important thing to note about these profile plots is that they are actually saved as several snapshots in time, and that's what this bar down the bottom here is. If we press play, we can see how it is that the simulation changes with time, and you can note that at the final condition for the simulation, there is actually this difference at the end of the flow line. So in general, what you want to do is to look at profile plots from the end of the time that you've simulated. This is particularly true when you're dealing with various transient phenomena, such as hydrate formation. So there are two more things that I'd like to show you in terms of these plots. The The first one is that you can actually edit them by right-clicking, Edit, Select, and that'll once again bring up this choice of variables. So we can say, let's include flow regime within this. We press OK, and you can see now we have flow regime, slugging at the inlet, and nice stratified flow throughout the majority of the flow line. And the final thing then is you can also edit, copy, and you can copy data. So what this does is it copies all the data that goes into making these figures, and you can paste it, for example, into Excel. You can then create your own figures. So here we can just quickly take a look at the holdup as a function of line length. Now what I'll also be putting up after this tutorial goes live is a couple of PowerPoint slides showing you how to present your Excel plots in a way which is much easier to read, and this is going to be something that's important for your final report. Okay, so that about wraps up tutorial 2. What we've done is to build a simple steady-state case within OLGA and run that successfully. What we'll be doing in the next tutorial is to make this case more complicated by adding in another well and connecting two fluids together and seeing how we actually blend them together.